Okay, let's dig into this. Welcome, everyone. In these deep dives, we try to pull out the key ideas from the sources you send us. And today, it's something, well, surprisingly practical. The math behind how much water crops actually use and lose. We're talking evapotranspiration.
Right. And if you happen to be wrestling with college-level math right now, maybe differentiation and integration specifically, you're about to see how those concepts aren't just textbook exercises. They have real impact way outside the classroom.
Exactly. We've got material here that connects calculus, believe it or not, directly to figuring out how thirsty plants are. So our goal here is really to understand how integration gets used in this whole evapotranspiration thing, and maybe more importantly, why it matters for keeping crops healthy and watered.
Yeah, what's really cool looking at these sources is seeing these, abstract math tools. They're not just theory, they're genuinely powerful for solving really practical hands-on problems, like managing water for agriculture, which is huge.
Totally. Okay, so let's start with the main idea. Evapotranspiration. The sources explain it's sort of a combo process, right? You've got water evaporating from the soil, from puddles, even wet leaves. That's the evapo part.
And then you've got the transpiration part. That's the water plants release themselves basically through tiny pores in their leaves, the stomata, kind of like plants sweating.
Yeah, like plant sweat. So ET, evapotranspiration, is the total water shuffling from the ground and plants up into the air.
Exactly. And the key thing is, this is always happening, but the speed, the rate it happens at, that changes constantly.
Okay, so think like a blistering, hot, windy afternoon versus a cool, damp morning.
Precisely. The rate of water loss will be totally different.
Right. So you have this rate of water loss, maybe in millimeters per day or something, but just knowing the speed right now isn't quite enough for a farmer, is it?
No, not really. You don't just need the instantaneous rate. You need the grand total, the amount of water lost over a useful time period.
Like over a whole day, or maybe a week, or the entire time the crop is growing.
Yeah, exactly that. You need to add up all those little bits of water loss, second by second, minute by minute, factoring in how the rate is bouncing around because of the weather.
Okay, and based on what we're seeing here, that's the cue for integration.
Yeah.
That's what it does, right? Takes a changing rate and gives you the total accumulation.
That's the core idea. You're integrating the rate of evapotranspiration over whatever time window you care about. Conceptually, you're summing up the tiny, instantaneous amounts of water being lost.
So what exactly is the function you're integrating? Is it just like water loss per hour?
It's essentially that, yeah. A rate of water volume loss, sometimes per unit area, over time. And the sources mention models things like the Penman-Monteith equation are famous ones that use environmental data to calculate that instantaneous rate.
What kind of data?
Things you'd expect: air temperature, humidity, how windy it is, how much sun is hitting the ground, all that gets crunched.
Okay, wait, so those models use temp, wind, sun to estimate the rate of water loss at any given moment?
Pretty much. They figure out the energy available for evaporation and also how much the plant itself is resisting water loss through those stomata. You could even say differentiation might play a role earlier, maybe in figuring out how sensitive that rate is to a small change in temperature, for instance.
Okay. So differentiation might help understand the race behavior, how it changes with variables, and then integration steps in to sum up that calculated rate over, say, 24 hours to give you the total water gone.
You got it. Integration turns all that complex, fluctuating environmental influence into one really useful number: the total volume of water lost.
And bringing it back to the farm.
Yeah.
Knowing that total loss is, well, everything for irrigation, isn't it?
Absolutely critical, because if you know how much water left the field via ET, you know almost exactly how much water you need to put back in. It tells you when to water and how much. Get it wrong.
If you add too much water, you're wasting it, maybe hurting the plants or causing runoff.
Right. And if you don't add enough, your crop yield suffers, plants get stressed, maybe even die. It's a fine balance.
So for you listening, maybe especially if you're dealing with calculus right now, when you see those integral symbols, they're not just scribbles on a page.
Not at all. They're incredibly powerful tools. They let us quantify really complex natural processes, turning these constantly changing rates into solid totals we can actually use, like figuring out how much water a field needs. Integration makes evaluating something dynamic like ET possible.
And that calculation directly impacts something as fundamental as crop hydration, water management, and ultimately, well, food production.
Yeah.
It's a pretty direct line from calculus class to the dinner table, in a way.
Definitely. And this ability, taking a rate, integrating it to find a total, it's fundamental everywhere, not just in agriculture. So many fields rely on this.
So maybe here's something to think about after this deep dive. If integration is quietly working behind the scenes to help manage water for plants, what other complex changing processes out there are being understood and managed because we have the mathematical tools like integration to sum things up? Where else is this math shaping our world without us even realizing it?
Yeah.